So you present first. Or you can, yeah, I'll send you the link. You can use the same as the previous one. Test. Yeah, I think it's good. You kind of external pointer. Okay. Here? Okay, for sure. Whenever you're ready. Oh, yeah. No, like this. Empty today. You get right? No, it's something that people will keep on coming and people will talk. Ah, okay. Please. You're gonna switch cookies, okay? What? Badly. Yeah. Hmm? He gives us a go ahead. He said like, wait, people get here. Who will first ask question? Thank you.
Yeah, thank you so much.
Careful for the audience.
Yeah. I'll turn it off.
That would be a very good.
I think everyone is taking early Thanksgiving break.
Yeah, unfortunately, today we'll have only one. So we'll start on.
Yeah.
Okay. Yeah, yeah. Good evening, guys. My name is Mansoor Bilad, the PhD students, and we're going to present this paper that was presented at Macro last year. It's very recent, and it's basically on compressing these large language models and introducing a new format to essentially do that. So hopefully at the end of today, like you will learn what is essentially a gap and a problem with current quantization approaches for large language models. And there's a smart and elegant way that they've introduced that tries to cater to that problem. And hopefully you will learn that at the end of today. So just for like housekeeping, you can interrupt us anytime, like during the presentation, and like ask questions. We want it to be like very interactive, and don't hold your questions like up until end. And the other thing is we have cookies that I have baked. So I have learned recently how to bake. So hopefully you will like it. They look ugly a little bit, but they taste nice, I think. Yeah. Give them the recipe. Oh yeah, I do. Okay, I'll tell you. Okay, so let's begin with here. Like we're just gonna give you some refresher. We are not going to go into like the basics of like neural networks. There have been like multiple talks by other fellows on like attention transformers, how they are trained, and there's like a lot of stuff that goes on in here. And you see, you're familiar with this architecture here. We just want to like show you the like just a refresher of like what we are interested in and what we want you to get something from today's talk. So it's like it's a 3-layer neural network, and it has these neurons, and those are the connections that we call them weights or parameters. And you have learned most of these training procedures like this page attention or flash attention, most of these other presentations that you have heard so far. We're not going to focus on that part. We're going to tell you today that what's problem with these current approaches of like once we train such a neural network. This is a very small toy example. In reality, they're like really huge and really massive, and you're going to see that today. So we're interested in how to store these models and how to save them, and what's the memory bottleneck that we are going to address today, and we're going to try to make you understand as well. So each parameter here, you see like these are like weighted edges, and they represent the importance of each neuron and how much it contributes to the output during inference. So, and each parameter is essentially stored in the memory because we need to work in the architecture domain, and we need to store them. So that bottleneck is here. Like usually, like we represent them with like 32-bit floating point numbers, and that essentially creates a huge like space for us to and a bottleneck so that we can address and make them smaller. So we'll talk about how to compress those models and make them like easier to use, like for edge devices and for like various applications that we can't do today. And we'll also like talk about this logarithmic number system that they have like kind of extended upon in this paper, and how they created a hardware or a way design for it. So this is a meme from some random Instagram post. You see, like we are very impressed with these language models and like how they are getting better like each passing day, and they like their reasoning capabilities, the amount of work that they can do, it's getting immensely powerful, and that's good for us because GPT 4.5 can like organize like your life and can give us advice on other stuff, can mentor us. There comes so like these models essentially like we just we interact with them on mostly on a daily basis, but what we don't see is what's happening behind the scenes and how much power, energy, and resources are actually utilized to make these inferences at one time, and how to make it that
quick and possible, and how costly they are. So hopefully, like just an icebreaker here. How many of you like actually tried to run any of these or like any other LLM on your local computer and try to make some inference locally? Great. Anyone else? Did you download it locally and run it on your computer? Okay, so I would expect 3 things if you did it. Either you had a compressed, a smaller version of some model, if you're running it on your laptop, or you use some API. Mhm. Great, great. Anyone else? So the reason why the rest of us haven't tried, or even if our fellow has tried, he has essentially worked with a very, very compressed, very small model, small like version of these big giant models. And the reason why we can't do it is because we don't have enough compute or available in our laptops. We don't have enough RAM to run it. And that's a huge roadblock. And we can't imagine how can we run these models locally on some edge devices that we wanted to. So to understand that, how like practically they need like several GPU clusters to run these models, and we still like face a lot of problem. So this is not like a tech bros like hobby problem that like let's create a small version of a huge model. We're talking about $1 billion industry that's actually interested in, and that is spending and investing like billions of dollars into create like formulating such ways to make them smaller, or to find some elegant ways to run or make some inference in runtime, like without these hardware overheads. So this is like to give you some context into like how big we are talking about. This is a Reddit post by OpenAI when they were releasing GPT-5, and they compare like kind of like the GPT models with different celestial bodies. It's funny and it's also terrifying as well. Like seeing how like from GPT-4 to 5, how much they have scaled and how much like they have like over parameterized these models. And we need to like and by the way, like the models, for example, that our fellow has tried, they're not even in this picture. Like you can't imagine how small capabilities that we have currently, and we need a way to find it. So these are like some of the these are for like comparison. They are not like actual figures, so they are like just for educational purposes to give you an idea of how big we're talking about. For example, GPT 4.5 and 5, they are like around like 5 trillion parameters. Like by parameters, we mean those weights or the connections that you saw in the earlier slide. And the amount of storage or memory that we need to store these parameters is like insane. It's like, if it's visible to you, it's like 18 terabytes of memory that's required to actually, like the ones that we're using making inference in runtime. OpenAI actually runs these on like tons of these GPU clusters because the size of the model itself is like 18 terabytes. So this is a huge problem that like the industry is facing, and we need two ways to actually solve this and make it like easier, or like for us to like for each for it to like make it accessible to like people, or like people like us, for example, like who can't like afford like these big GPU clusters. So we need ways to find it. We'll have to tell you how we are going to do it. Oops.
Okay. Now we'll talk about different types of on how we can compress the model. So usually people use 3 types of compression. The first type is called pruning. So in this method, we try to kind of compress the model by eliminating the weights or the attention heads that have like little impact on the output. So there are 2 types of pruning. The first type is structured. In this type, we remove like the whole attention heads in the model, while in unstructured pruning, we just remove some weights that have like little impact on the model. And the main advantage is that it's pretty easy to implement, and it doesn't require to retrain the model. The second approach is called distillation. So in this approach, we have a student and a teacher. And so we try to train a student so he can like imitate the teacher. So we can see like this example in our real life. So like we go to the lectures and just trying to like get some knowledge. And in this method, the main advantage is that it doesn't change the initial architecture, but the main drawback is that we have to retrain the model again. And to retrain the model again, we need to have the initial data set. And to train this model again, it also requires some additional resources that not everybody has. And yeah, and the next approach is called quantization. So we'll talk about this approach in this paper. And in this approach allows us to reduce the precision of the model. And it also allows us to make the model more compact. And at the same time, it also like allows us to preserve the accuracy. So by quantizing the model, we can port those models into smaller devices. And quantization allows us to reduce the overhead, and at the same time, it requires less the computational resources. And yeah, it's a pretty convenient approach to reduce the models. So as we previously talked, now we'll talk about the model quantization. So in the previous slide, you could see that we had like different large language models, such as GPT from OpenAI, Claude from Claude Opus from the Anthropic, and all those models. And they have a lot of like billion parameters. And at the same time, they have a lot of like different values. And in order to store these models, we need a lot of data. So for example, GPT 4.5, it has 4.5 like billion parameters, trillion parameters. And at the same time, it requires us to have 18 terabytes of storage. While recently released, the GPT-5 has like 3.5 trillion parameters, and it requires us to have 14 terabytes of storage. And Opus has like 2 trillion parameters and has like 8 terabytes of memory. And on the left picture, you can see the values that are stored in the original dimension. So it's floating point 32. And on the right picture, you can see the quantized models, and they're being stored in the type of integer 8. So as you can see, quantization allowed us to reduce the size of the model almost four times. Like, for example, initial size was 18 terabytes for the GPT 4.5, and the like outcome was like about 4 terabytes. The same for the GPT-5, it was like 14 terabytes initially, and now it became like 3.5. And the same for the Claude, so it was like 8 terabytes initially and became 2 terabytes. So as you can see, like quantization is like a pretty efficient approach to reduce the size of the model, but at the same time, we can keep the initial accuracy and don't really change the whole model from scratch. And now we'll talk about how this quantization approach works. So the first step is that we need to have some values from the activations and weights. And this approach consists of 3 different steps. So the first step is called scale. So in this example, we'll go from floating point 32 into integer 8. And integer 8, it has 256 values because it's 2 to the point of 8. And in order to do that, the first step will be the scale. So we try to convert the bigger value to the smaller value. And the first step is just to take the maximum and the minimum values of activations from our model. And then we have to divide this this data into the scale that we want to receive. So in our case, it's integer 8, so it will be 255. And then the next step is called rounding. And in this step, we have to round our initial data type to the closest that we can achieve to the one that we want to receive. Yeah. And based on that, we can just convert from our initial floating point 32 into integer 8. And this allows us to keep the same accuracy and keep the same model. But at the same time, there arises different challenges, because the first challenge is that if the values are too big or too small, so we have outliers and we have to handle them. And we'll talk about how we handle the outliers later in this presentation. And yeah, and Mansoor will continue the slide.
Yeah, now that we learned how quantization works, our standard quantization works, it comes with some inherent limitations that we're going to talk about today. And so keeping in view the previous example that you just saw, when we quantized 32 floating point 32 numbers into integer 8 or into integer 4, how much precision did we lose during this process, and what was the error that we saw? That's one thing that we need to consider. And the second thing is, in this example, if you see that in floating point 32, they're very small numbers that are near 0. And when we quantize it into integer 8 or into integer 4, most of these values are essentially getting rounded off to 0. And that doesn't mean anything, and we are losing a lot of inference accuracy that the model inherently has. So this is again just for educational purposes. It may not be correct, but the idea here is for near 0 values, we lose a lot of precision with the standard quantization approaches. And so the other thing that people observed is, if you see this plot, for example, and when you try to analyze the distribution of the weights that these neural networks have, for example, CNNs, or for example, ResNet or VGG, or even for LLMs, they have a lot of values that are near, very close to 0, but they still help the model in making inference and in making correct our guesses or approximations about the output. And we can't simply round them off to 0 and say, oh, we are done. But that's not how it works. And we need to keep this thing in mind, that we need to expect a lot of near 0 values, or we need the other problem with the standard quantization is that we currently do is, because we do uniform binning, we have a discrete amount of bins that we can map from the floating point 32 to the integer domain. So we have very discrete amount of domains or bins that we can quantize to. And so the rest of for example, the dark red that you're seeing, they're just wasted and they're not being used. So it's just show that how uniform binning is a serious problem with the current quantization approaches. And so this makes us think about some smarter ways to actually come up with some ways that cater to this problem and overall. So for this, we come to the our high school maths or calculus. We learned about some nonlinear functions, and we think they might be interesting to us, and they might solve our problem that we have when we map from floating point 32 to some integer domain, and the amount of precision that we lose, and also the amount of the inherent distribution of these 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 weights is basically really diverse, and it is like either clustered near zero, like just keep that in mind, or they have like a lot of outliers that we will see later on. So can you think of like some nonlinear function, any nonlinear function that you have learned so far, and can we use that? Anyone? Any nonlinear function? Logarithms? Okay, you got to the page. Okay, so logs definitely. I don't want to give you some answer.
In your second or third slides.
Okay, you're smart. Oh, cookies, yeah. By the way, the people who just came, these are, we baked these cookies, so just give us feedback as well at the end. So log function is very interesting, and we think like another problem that we didn't discuss here, but we had that problem of because like with neural networks, we're doing a lot of like multiplication, like everything is like a linear combination basically, so multiplications and additions. And from our computer architecture course, we know that multiplication is really difficult and it's really hard at a hardware level. And we need a lot of transistors and power to actually do that multiplication. So the log function is really interesting because it makes multiplication really easier, and it turns into addition over here. So for example, when you apply a log to like x, the product of x and y, it turns into addition, and it's really easier at the hardware level. But this is not inherently the problem that you wanted to solve here, but we are getting it for free. Here's how the log function looks. So if you like look closer into the plot, we see like some interesting properties of logarithmic function here. The near zero values, they get like a higher range in the new domain that we want to map it to, and the higher values that are not really interesting to us, they get like shrink together, and we still map, like for example, the numbers from like 1 to 1,000 into from 1 to 10, and we still like keep a lot of precision here. So that's why log function is really interesting, and this leads us to the crux of today's discussion on what is on the logarithmic number system that has been like recently introduced. Log function is like has been there like since 1970s. Like people have been using it in signal processing for like quantization and like for several like for most of these purposes. But we'll talk about LNS, and LNS is like still like very much under research, and it's not like implemented in our today's hardware, but we see like a lot of room that we can like make use of it. So what actually LNS or what log function does? So we don't store the original number, the original parameter value that we have. For example, here is x. We don't store x, but we store its log. We take its log and we store a into the memory, and so essentially like we are storing the low precision like version of this big like high precision number x, and we can decode it like really easily by taking like anti-log or like to the power like that number. This is how like this is like the basic of LNS. LNS has been like recently people have been trying to like use LNS for LLMs. So LLMs have some interesting properties that are different from our standard neural networks. For example, CNN, like ResNet, VGG, or something. Here, like the authors of this paper, their contribution is like twofold. They first like prove this argument that you shouldn't treat LLMs and neural networks the same way, and you shouldn't quantize them the same way, because inherently they have different distribution, and they have the nature of these weights and activations is really different for both. And they prove it by these two. Okay, let me show you. So in this plot, what you're seeing is they use LNS, they quantized basically like the parameter. This is for like Llama 2 basically. So they quantized Llama 2 model with LNS and with floating point 8. So they're both stored in 8-bit precision. What we're seeing here is in the middle, you see there's a spike near 0, and that spike basically refers to how much like the distribution is like clustered for LNS and not for 14.8. So this is like an observation that they need to cater to and make these this range like a little bit wider, so that like we don't lose precision near zero. And the other thing that like interesting that they observe is when they compare like large language models with like other neural networks, they saw there is like a different pattern in the outliers that are out there. So the blue plots are they basically like the blue curve. It refers to like the range of like outliers that are there in LLMs, and the red one refers to the outliers that are there in ResNet or like other neural networks. So this like they kind of like establish this argument that because these two distributions are really different, and they proved it like so like by comparing these two, this makes them like go further and dig deeper into like what actually those distributions look like. So like this plot I'm seeing this looks really small. So this plot shows basically like the weights or parameters of a language model that they have like the plotted to show that there are like spikes like for activation and for weights. So like on the left side you're seeing the activation, on the right side these are the weights of like llama 2. Like they are like taking llama 2 as a example here, and they're trying to prove point here. So you're seeing that there are like spikes around like on the channel axis and on the token axis. Like so think of like these activations or weights as stored as a tensor, like where the rows are the tokens and columns are the channels. Like think of it like in a computer vision way, like any way you want to imagine. And you see that there are these spikes, and they are really interesting, and because they need to be catered for. The other thing that they also observe, this is the fourth thing basically, that they do to prove a point that LLMs have a different behavior, and that's why standard LNS is not good for LLMs. Here they observe that most of the bins, the quantization bins that are in the LNS, they're not being used basically. So you're seeing, for example, like above zero, like most of these, like they're not being used at all. But you still have like in the memory, like you still have like space for storing values. But just imagine like, but you can't store like they're always like zero, and you're wasting a lot of like memory here, and you should look into like this particular part of it. So it turns out that they prove a point, and that LLMs have a different behavior, and we'll have going to tell you how to deal with it.
Okay. Well, now we'll talk about how our framework works. So in this framework, we have different components. The first component is analyzer. So analyzer collects the data such as activations and weights from the evaluation data set. And then it goes into decider. Then decider is used to kind of determine like what parameters should be used, and what kind of data or hyperparameters we should adjust. And then we can introduce the auto evaluator, and this component allows us to automatically adapt the to outliers and like different changes throughout the process. So yeah, so like this overall like this is a pipeline of the framework that is being used to save the data to the GPU. And overall, there is also like a second part where we do the same thing, but after that, we use this data to send it to the hardware using like DRAM. And yeah, and this approach was implemented using like 3 different steps. So the first step is called data format. So in this step, we'll talk about on how to like convert the data from like for like values that are below the outlier or higher than the outlier. In the next level, it's called data flow. We'll talk about on how to perform like different operations such as matrix multiplication. And in the final slide, we'll talk about the architecture. So in this slide, we'll talk about how this framework was implemented on the FPGA. Yeah, and we'll start from the data flow. So imagine that we have some data exponent like with different beans, and these beans, as you can see, like this gray area, it means that it's like an empty space that is not used. And the main problem is that means that we are wasting a lot of space, and there are no like activation of values in this range. So in order to solve this problem, we introduced the quantized bit relocation. So quantized bit relocation allows us to distribute those activation values, so it would like align more closely to the new LLM distribution. And like, and from the left picture, you can see that we had some values like minus 1, 0, 0, 1, 1, 2, and QBR encodes those values into a new representation that allows us to fill those unused space. And as the output, we'll get the offset, step, and delta. So offset determines how downward we should like move those values. Step determines the distance between those beans, and delta determines how like we should like distribute those values. Yeah, and the second approach is called bit unpacking. So it's worth to mention that previous approach QBR is being used for the values that are below the outlier, while the bit unpacking is being used for the values that are greater than the outlier. And in the first picture, we can see like a storage with 32 bits, and we have like 4 different elements, and these elements have a size like 8 bits. And the main goal of bit unpacking is that because it's designed for the outliers, it means that the data, these values are too big. So we have to like give preference for the large numbers. So we have to give more space to the fraction part. And to do that, we have to introduce the bit unpacking. So in this slide, we can see that the new distribution shows us that we assigned 30 bits to the first 3 elements. So this allows us to store the outliers more precisely. And yeah, and basically it allows us to handle outliers throughout like the process of the LNS. Yeah.
Yeah, now that we'll learn like how to store essentially or create some new dynamic formatting for the data, we need to now work with the data, because it's not just like we want to store the values or have a smart way to store it. We also want some way to work with these values and how to implement it actually in the hardware, because essentially remember that like for LLMs or for neural networks, the ultimate goal is matrix multiplication or multiplication that we want to do. And because we messed up with, like, we create some new formatting for the data, how to store it, and think of it like you had a tensor that's like 100 by 20 dimensional tensor, and some of these columns in this tensor, they were dynamically reformatted. They had outliers, the rest were fine. So their idea is like apply only this data formatting, either QBR, like where you dynamically relocate those bins, or you unpack those bits. Do it only for those columns in the weight tensor or the activation tensor. Do it only for those columns which have outliers or very low precision numbers, like very small numbers. So this is like like essentially the matrix is not uniform at all. The tensor is going to behave differently. So there is a way that like people have been like doing to do matrix multiplication, because again, remember how huge or how bigger these models are. Like we are talking about terabytes of memory, or like even like gigabytes. It's really huge memory. And when you want to perform matrix multiplication, we saw some presentations on like matrix multiplication. There are like various ways to do it. And also like there was a lecture on like blocking, and like during the caching lecture, like how we saw that you can like create blocks and perform matrix multiplication. But here they introduce like they work with another form of way to do matrix multiplication, and that's by systolic arrays. So systolic arrays is a new thing. I wasn't familiar with it back then, and maybe you are not as well. So this is just illustration of like how we do matrix multiplication, and there are tons of ways to do it. But let's talk about what is like a systolic array, and like it's I understand it's like pretty hard to understand or consume, so I'll try my best to convey it. So think of it like you have the two matrices, basically two tensors. You have the weight tensor and you have the activation tensor, or the input basically. You want to perform matrix multiplication like in this slide, like you're multiplying W matrix with X is basically a vector, and you're going to do this multiplication. So imagine like W is the one on the top, like with 1, 2, 3, 4, and activations or input is basically the one on the left, the green one. So the green one and the blue one, they are going to get multiplied. This is just a simple 2x2 example of how systolic arrays work. And so the idea about like behind systolic arrays is how like it comes from like biology, basically, like how like hertz beat and how like it's like rhythmic, and it does like one step at a time. So they get like inspiration from like biology, or like how like hertz pumps or something. You have two matrices, the blue one and the green one. You want to multiply them. So the way like this is implemented is it's done like one step at a time. So you don't store the entire matrix at a time. So like the blue one, or the weight matrix, or the activation, the green one, you don't store them in the memory. You just take one value, like a flow from each of them at a time, and pass it through. The red one is basically called like the processing elements, where they do the actual multiplication. So at each cycle, so it's like implemented in cycles. At each cycle, one element comes from both, a column from the weight matrix and a row from the activation matrix, from the green one. So one value comes at a time, and they get multiplied, and the output gets only stored. So you're not storing the entire matrix, but you're storing. So let's see like how it will look. Once like 3 and B come inside, like this processing element, that's like 0, 0 processing element, they get multiplied, the values are stored, and they're processed. So that multiplication is not going to take place again. Similarly, like it keeps on flowing, like both like row wise and column wise. So they both like come one step at a time. They get multiplied, and then their result is stored only. So if we keep on doing it like until like the entire row or column is finished, you store the value, and that's the end output. So we got A here, basically. That's like the product of like the first row and the first column. Similarly, this is kept on doing like for one cycle at a time, and you get the outputs, and you wait like until basically like when the row, that particular row or column gets like processed completely. So each one of these red ones is basically called a processing element. So it's a buzzword, just keep it in mind, processing element. So here, this is cycle 5, and we are done. So we multiplied matrix, like the green one and the blue one, in like 6 cycles. Imagine how it makes life easier when you are dealing with like matrices that have like billions of parameters, or like or even bigger. So you do it like one step at a time, and this is how like actually they're being implemented. Like our like current LLMs, they do like inference based on systolic arrays. This is not their contribution by these authors. But they found, because they reformatted the data, they have to use like some way to do matrix multiplication. That's why we introduced systolic arrays to you. So this is how they do it basically. We've talked about like the green one and the blue one, like those matrices here. On the top, you're seeing the weight matrix, weight buffers, what they call, and on the left is the activations, and in the middle, they are like SPs basically. They're called like, or super processing elements, because they don't take like one row at a time, but they take a block of like rows at a time to make it like more easier. I don't think there exists something like non-systolic array. If I don't know. Yeah, I only know systolic array.
Those red lines, right?
What?
Green SP.
Mm-hmm.
You can go back to previous.
Yeah.
Yeah. If you go back to the previous, then yeah, that slide, right?
Mhm.
There's A and B if you see on any cycle.
Mhm.
So now to have PEs, like processing elements that you mentioned, right? So in systolic arrays, they are broadcasted actually. So one shot, you go one instruction, they load all of them together to all the systolic arrays in the row form. And then now, similar happens in the column form. But that doesn't happen in non-systolic array design. Actually, that's the
Okay. Oh,
difference.
that's great. Thank
Broadcasting
you.
nature, right? In both the ways. Now, if you go back to next slide, it
Mhm.
shows that there is a connectivity between them. Yeah. So all those reds, right, in between SPs, they are all those broadcasts. So it supports that broadcast all the way. A is being broadcasted to all the rows of your SPs and then columns, such that because to do matrix multiplication, right, you need A versus all B's. That's why you have those red connected actually. Otherwise, in a non-systolic array design, you don't have that connection. And you're wasting time loading that A again and again back.
Oh, that's interesting. Interesting. Yeah. Thank you for adding that. So like the idea, I have like everyone heard Naeem.
That's a broadcast nature. Because GPUs natively don't have that type. Very few of them have it. The red connection.
Okay, great. Yeah. Thank you for addition. So as we have learned, or you might have heard like Naeem. So like that's another way of doing this like matrix multiplication, and it makes it easier because you don't need to load it every time, right? Thank you. So here, like they do it like block wise. So another thing that's like worth mentioning here is on the left side, you see like these circles and these triangles, the red triangles. What they want to show here is the circle ones are the ones all those columns that they don't have outliers. They are just represented in like in this Shannon format like of LNS. But the like the red triangles, they are the ones that have outliers and that got like reformatted basically either via QBR like with like quantized bit relocated or bit unpacking, like you're storing like in the same space you're storing like fewer numbers, but they're like very high precision numbers basically. Like in 32 bits you're storing 3 numbers only rather than 4. So these are those columns basically. And similarly, like this is just for like demonstration here, and they do it like block wise. So they take like a block of rows and block of columns to do like this systolic array multiplication rather than just like one row at a time. And they call it like super PEs basically. And you get the output on the right side, the one that we saw earlier, the red matrix. And Vlad's going to tell you how they implemented in the architecture.
Yeah, so now we'll talk about the architecture part. And so I'd like to outline some points. So the first point is that mixed precision processing elements is like for LNS arithmetic. So it means that we can switch between like high precision and low precision modes on the fly. And also we use like elastic buffering and data flow to like store and like reorder the blocks. So like our systolic array is being fed by the elastic buffer, and we also put the output into elastic buffers. And adaptive scheduling also keeps the pipeline fully utilized. So we would not have like time where there is no like any processing. There is no like any workload. So there was no like wasted computation time. So in the architecture part, they have adaptive scheduler scoreboard, and yeah, so scoreboard stores like which values are prime or which values are normal. So prime values is just values that are higher than the outlier, and adaptive scheduler allows us to kind of manage those processing elements and at the same time synchronize the process. And we also have non-prime blocks and prime blocks and weights. And besides that, we have elastic buffers and our systolic array. We use them as an input for the systolic array. So elastic buffers is like a temporary array. It stores the normal values, and it's also able to do the bit unpacking process. So it's able to align our like outliers to the new distribution, and it's also able to synchronize the process. So you would have like different values with different precision, but they will be synchronized in the elastic buffer. And in the center, we have the systolic array that we described previously. And in this systolic array, we do like different operations such as addition, multiplication, and in terms of LNS, multiplication is pretty easy because it's just an addition in a logarithm, and it allows us to save some compute power and make the computation faster. Yeah, and also like in those, and as the output, we get the accumulated sum of these functions, and yeah, and we also store them into elastic buffer. Yeah, and besides that, we also have like run-in max, which determines the maximum values of this of the output in the real time, and this allows us to kind of handle the output and handle the outliers as well. And for the experiments part, they used like 4 different models, such as Llama, Bloom, GPT, and OPT, and they tried these models on the zero-shot benchmarks. So zero-shot means that the model has not been like trained on this data set before, and we also like tried like different state-of-the-art methods such as zero quant and smooth quant. And we also tried to compare our approach with like different quantization approaches, such as popular, such as floating point 8 or integer 8. And yeah, and for the metrics we used like accuracy and like a perplexity. And for the task generation, we used like the generation part. And yeah, so we used like 7 data sets, and all of them like zero-shot NLP tasks. And for the hardware, they used the FPGA that is called Xilinx. And for the IDE, they used Vivado. And yeah, and they use like 7 popular benchmarks, and they also try to calculate the like performance on those benchmarks, as well as like energy efficiency, and how like our approach will show, and later our approach will show on how like those models are more efficient on those benchmarks. Yeah, and so it's worth to mention that the authors propose 2 types of optimization levels. The first level is that we just take only the data dynamic approach. So this allows us to kind of isolate and determine how like our new data format allows us, how it improves or decreases the overall performance of the model. And the second approach is called dynamic data format, but in this case, we also use the scheduler. And the scheduler adapts dynamically, and in the results, it will bring us about like 3% more inaccuracy. So overall, it's worth to use the scheduler.
Oh, they perform like different experiments with, as Vedat mentioned, like different LLMs and on different tasks. Basically, they're like primarily two types of tasks that they experimented with basically. And like, so the first one is basically the rows, like the columns that you see here, like for example, Lambda, Pika, like these are benchmark data sets for accuracy measurement of LLMs basically. So the way that they did is basically they took, like, for example, the unquantized LLM and perform zero-shot accuracy analysis on these different data sets, and they quantize the same LLM using this LNS format, the dynamic LNS format, and then they compare the results for both. And it was like the other approaches, for example, they did like a massive benchmarking, and we selected a few of them here just to show. And their approach was like actually like better, and in terms of like getting good accuracy of like zero-shot accuracy of predictions. And also the last one that you are seeing is the PPL is another benchmark. It's for it's for like generation tasks basically. So they did like for accuracy measurement, like, and for language generation tasks. The rows are like basically different types of quantization techniques. They did like a lot of benchmarking and on different language models as well. So like Llama, OPT. And so you're seeing here, for example, the bold ones here, they indicate like their approach, like the last three rows here, they were like a pretty good, like compared to the standard floating point quantization, or like the standard, for example, integer quantization, or there are other like quantization approaches apart from these, and they were like pretty good in terms of getting like better like let's say like reproducing good results out of that. And method was good. It's very strong.
Yeah, and overall, like as you can see, like from the results, our proposed framework handles the outliers pretty effectively. And one of the strengths of the paper as well is that they propose like 3 different methods, such as data format, data flow, and architecture. And overall, they use like a lot of different benchmarks, large models, and yeah, and like this coverage was pretty extensive, and it also has like a minimal overhead on the architecture part. And as the weaknesses of this paper is that it relies like on a fly collaboration, is that these like parameters have been pre-computed on the evaluation data set. And the main disadvantage is that it's not that dynamically adaptable, like for the changing data sets. And it was also like tested only on the FPGA. And it's also worth to test on the real GPUs. And yeah, and overall, like it was not like really research on how these dynamic modules are being used, and there is also like they didn't describe on how like this scheduler will affect the performance. Yeah, and
okay. So hopefully, like today, like we were able to communicate the the main like crux of the paper. We definitely like skip some really like niche details, or like implementation details, or like they have the whole like entire like pseudocode and the algorithm to do it, and also like implement a bunch of like other implementation steps that we just wanted to wanted you to get with this takeaway message that like the first thing that like I learned basically is like diagnose the problem well, and that's what they did like before. Like I know like it's still like not very precise. It still has some flaws. For example, we just mentioned the weaknesses. That they didn't compare like did a massive comparison between like different language models, different neural networks. They just like picked like made basically pick and choose of like two other neural networks, ResNet, VGG, and Llama, OPT. That's all. But that's not all. They have like very different behaviors. For example, Opus from Claude has a very different behavior. Mistral, like recently, like people reported that like it has like, I think there were some other talks that people mentioned as well, that these language models inherently, because they have like, they are architecturally different somehow, and in terms of their training data. So it needs a massive amount of good and unbiased evaluation first and analysis of like how the distributions look like and how to understand well. And that's maybe why, because they were not able to like get a near perfect accuracy. But still, like apart from that, like quantization or like dynamic, making things dynamic essentially is like is the way. Like there's no uniform and standard way to do anything basically. And they can also be like maybe like tweaked or modified for different LLMs. Like it doesn't need to be essentially applicable to all LLMs. If like, because they also observe the same trend as well. Like when they compared, for example, Llama 2 and OPT, they quantized these two, they got like very different results. And it shows that like their analysis is in itself like not really objective, or like it's not like really comparable, or that like or universally can be applied. But it's still open area of research, and they just did some good job of understanding the problem first and coming up with some way to deal with that. So like making things dynamic, I think that's the key takeaway message. And also like yeah, like for outliers. And another thing that I think we missed here to mention here is when we were talking about bit unpacking, like remember like, oh yeah, I can show you. So like when they were doing bit unpacking of like storing 3 numbers for 32-bit space, and each with a 10-bit size, they were wasting memory like 2 bits. And when you scale that up to these billions of parameter model, they still like are pretty much consuming or wasting memory over there, because they're not like using 2 bits and just scale it to like trillions of parameters, and you'll see like how it affects. But nonetheless, yeah, it's a good way and approach to do, and I think we learned something from it. And we'll also gonna ask you some questions if you want to, please.
Yeah, we try to not make the discussions hard. So the first question will be, why do you think like these low bit models, like low bit quantization methods, they like struggle with LLMs? Like any thoughts? Like yeah, like
like there is less difference between the range of the input values, so they mostly combine to 0 and they're more similar to each other.
okay, yeah, sure.
When the quantization is the first order, I think 4 being converted to 48. It's like weightless. We're already changing the entire model. Then rather than the weight context changes, and then the inference changes.
Giving.
I expected more. You have to correct me first.
We're gonna see all.
I'll take one. It's good.
Anyone wants to add
Everyone
something
should
else?
take.
Can we do scaling based on the range that, based on the input range, so that's how we can improve the quantization?
Yeah, scaling is what they also like in standard quantization, scaling is done actually, but there still loses specification. This question is basically like, can we like scale it to like?
So based on the range, we do the scaling. Is it possible?
That's what like strength quantization.
Yeah.
But it still loses like a lot of precision. And there is like there's a scale factor that is found.
Yeah, I saw that.
It's based on the equation of the main man.
Yeah. Yeah, you have like all like different activation functions. They have like log normal distribution and have outliers, and sometimes values are not like represented accurately. And what are like the two main components that we discussed in data format, like on how we can like represent the data? There were like two methods. Yeah. Yeah, where we like try to, we have like two beans.
Synchronic metric.
Yeah, so we talked about the quantization, relocation, and bit unpacking, and it allows us to get like low precision with the high accuracy. And what is the main advantage of using the LNS for the LLMs? What do you think?
We are able to represent complex numbers with encoding in simpler format.
Yeah, and also like in terms of cost, like why is it better? Like, so like usually you have to do multiplication, right? But in terms of logarithm,
You do addition.
yeah, you're right. Okay.
But that comes with nuances. You have to convert your compute and effort. That comes with nuances, like you have to convert your principal processing elements that you mentioned to behave as adders. That changes entire data path, and that there is no adaptability to the existing machines whatsoever. Correct? I don't think this fits to the entire existing machines. It doesn't. Right? Yeah. Also, even if you just do quantization, doesn't work out because today's software or compiler doesn't understand that, right? Representation.
They're messing up with the representations of the representations. And they like did like experiments with FPGA. This is not like objective basically, I think it's still it's hardware.
Yeah, and they also like in the implementation section they talked about that they had to use like hook functions because and because like initial library like Query doesn't support these functions.
You have used 2x2 matrix for matrix multiplication, right? What if it has a big matrix like with complex numbers? Does it affect the efficiency or something? Yeah, high precision. Yeah.
Operates the same way. Like when if like how big the metric is, what they do is they do it blockwise. Not like one row, one column. But it doesn't like it's the standard way to do like how story management. It doesn't depend on how big the values are, how big the numbers are. Even if they're like integer representation or foreign representation, it just perform each processing element performs one job, and that's perfect.
Yeah, like you're right. Like LNS makes multiplication easier because you just use the addition operation in the log domain, and yeah, okay, and that's it. Thank you.
Always been open.
Data format.
Textual like most of the because there is still like the architectural level is such as well. This was like the main thing. That's still like very much over. It is not maybe scalable. Apart from that, like the dynamics formatting of the data. Can we repeat that? Any of the kids probably this probably change this. Really the universal this number really there.
solid एक तरफ weighted और एक तरफ unweighted.
Yeah, that's a very interesting question. I think we haven't thought about that. Even maybe the analysis comparison of hardware. I hope you guys like.
They talked about ASICs, but ASIC.
GPU ASIC.
Yeah.
Like how like any particular hardware, how this is spelling.
Yeah, they didn't do this part.
So they didn't change. No, so the scaling that we talked about earlier, I think that we are very the conclusion here. Here, talking about the standard quantization, like how standard quantization happens. But in LNS, it's like those floating point numbers, original like weight tensor, they are like mapped using log function, and you get a new weight tensor, and you work with the new tensor basically. So they are not like essentially like rescale gain or it is trees like we converted the log map to tensor and then do the reformatting of that. So whenever, for example, we have a new model that we want to quantize, like using that approach, like what they do is they first take the model that they made, the model for each layer, they take like a basic spaces of each like, column in the matrix for each layer, and then they like the outliers, like a column that they don't have, column that they don't have, and that's how like they do they make it like scalable or maybe like immutable or different hardware. But I don't think like it maybe relates to like how it's going to get implemented. They do like same implementation for each part, and they do comparison. I think they didn't show the results of the PGA, GPU, and ASIC picture like the hardware, but they still have wanted to make a comparison like there or they get the same goal of this patient and they didn't change it. But they did like this custom function, like the hook function, like the
Yeah.
for the ID going on with I hope that yeah. Yeah.
Okay.
Yeah. Upper. Actually. We didn't play the results here.
Yeah, so like
They,
save
they,
was,
they did comparison, and FPGA was like, I don't know, maybe because
yeah, and it's also like energy efficient.
in terms of energy efficiency as well.
Yeah, so like they try to like measure the energy efficiency, and they mainly did it on the FPGA. So like we had some tables before, but they're not here anymore. Yeah, and it showed that like this framework was able to be like 3 times more energy efficient. So it's able to process like 3 times as more tokens by using like the same energy consumption. And yeah, but they didn't like test it on the GPU. So it's like I think it's like will be in their future work. But it was, but it's not like, but it's only to run the models.
So as far as your question was like, there are the different GPU. But the problem is actually
Thank you very much.
Yeah, so again, I think we have like concerned about yeah, probably like they used the PJ because of this historical array, so like it's, at the same time it's able to be like more energy efficient, and but it's not like that they did work on the GPU, so yeah, maybe like it will be like in their future work.
data format. That was hoping like the that will show really data format. You have a question?
Can you go back to slide 17? So in the input buffer, you told that the outliers are represented on the right and the other numbers are represented on the left, right? And how can that be same on the output buffer after the operation? It cannot be the same, right? If you are performing multiplication, matrix multiplication, or any operation you perform there, it cannot be the same representation on the output buffer.
Nice catch. It's just for demonstration purposes. Like these outlier columns, they can be anywhere in this tensor, and they're like random. You don't know. Just want to like make this distinction of like which columns are have outliers, which ones don't. And definitely when you do matrix multiplication, you can also get as output outliers as well. So because you like multiply, it's a given combination of like any big numbers, you can still get outliers at the output. What they want to demonstrate here is like in these tensors, you can have like you can have both basically. And they focus specifically on the columns of the outliers. But they can be like it's just for like
but normally they will be scattered around, right?
Yeah, they will be. It's because it's random. Even the order itself is like these columns. They can be anywhere.
Okay.
Yeah, it's just like according to that.
Or you can share your risk.
That's the reason why. Do you have some more cooking in the back?
Unfortunately, that's all. So. If you give me good feedback, I will.
That's really good.
Today there will be no voting, or you can just vote him.
Maybe we can do catering for our presentation. How much cookies do you want? We'll order from him.
Maybe voting on presentation versus
I see many people online. Guys, do you have any questions?
Let's see here. We go. Let's see.
Yes, we are done for today. As I said, the first presenter had some health issues, so we scheduled her probably to the last day, right? So I'd like to take attendance physically. So if you have a piece of paper, like to take the names